undergraduate program in Electrical and Electronics Engineering and a postgraduate program in Power Electronics and Drive. We also have a recognized research center in a department. So with this short note, I would like to request our advisor, Electrical Sciences, Dr. G. Sambandan, to brief about the SGTP and also introduce our speaker. So,
Thank you, Dana. Good morning to everybody. We are starting this STTP sponsored by AICT. I'll just brief about the background of the STTP. In the energy sector, two key phrases are becoming the focus of international and national policies: grid resilience and cyber security for cyber physical grid. Resilience of the grid is often associated with making the grid able to withstand and recover from severe weather and physical events. But resilience should also include the ability of the cyber physical grid to withstand and recover from malicious and inadvertent cyber events. Resilience of the overall cyber physical system must include tightly entwined cyber security technologies and physical asset engineering and operations combined with risk management to ensure appropriate levels of mitigation strategies. The proposed STTP aims to explore the challenges to resilience of the renewable energy integrated smart grid to cyber threats. As you know, we have done the first phase of this program between 27th to July to 1st August with the research approach. Now from 17th August to 22nd August, we are inviting experts from international locations to share their experiences and the international practices. And we have the third phase starting from 7th September to 12th September with speakers from industry sharing their experiences. Eminent domain experts from various organizations and industries will share their experience and expertise. The program will be conducted in an interactive environment, providing greater scope for discussion. Now, I take pleasure in introducing Dr. Andrew West. Dr. Andrew West is a software engineer with qualification in electrical engineering, computer science, and psychology. He has worked as a SCADA engineer for over 35 years, with majority of that time in electric utilities and substation automation applications, working for utilities, equipment vendors, integrators, and as a consultant, including involvement with ICS cybersecurity since 2004. Since 1996, he has participated in the development of IEC and IEEE standards for SCADA and power grid automation. He chairs the DNP technical committees and is spokesperson for the committee responsible for IEC 60870-5-101 and 104. He is a member of the committee responsible for IEC 61850. He currently holds the position of Regional Director with Subnet Solutions, a system company focused on electricity grid data and cybersecurity. He is based in Brisbane, Queensland, Australia. Now I hand over the platform to Dr. Andrew West. Sir.
Thank you very much for that introduction, Dr. Sambandan, and good morning to all of you. I'd like to make a request as we start that you could all please keep your microphones muted unless you need to speak, just to reduce the amount of background noise and interference. During a test that we made of this conferencing system last week, we encountered a few issues with breakup of the audio. So if this occurs, can I ask Dr. Sambandan to interrupt me if we need to go back and repeat anything? But hopefully we have addressed the issues and everything will be straightforward and work okay. So, as Dr. Samban has announced, I work for Subnet Solutions. We're a software company, but we deal with the grid. And our company name is a contraction of Substation Networks. But it's also, I think, a clever name for anybody involved with IT and communications. Today, I plan to talk about some perspective that I have watching the development of grid automation, the smart grid, and the introduction of cybersecurity into this space and the adoption of standards. What I will be talking about is mostly my understanding and my interpretation. That does not necessarily mean that it is the truth. And if I say something that you disagree with strongly, let's talk about that because we have a different perspective. And that's good. We are here to learn from each other. Also, I might say something that will resonate with you as a good idea. And many of these ideas have come up previously, and I will later in this presentation talk about some of the history that we have gone through and how we are progressively becoming quicker at learning from our past. And I'm going to try and highlight a few things in that area. So the topics I will talk about, I'll be talking about the smart grid and cybersecurity as it relates to the power grid, the role and the purpose of standards, particularly the protocol standards, because that is my background. And then, as I said, we'll talk about learning from history. And throughout this, I will make reference to management of data and access to data and controlling that data, both with respect to how the data is used, the cybersecurity of the data, and how the standards use that data. Also, you have already realized that I speak with a foreign accent. So sometimes I might say something that is difficult to understand. Again, if it is important, please interrupt the process and we'll clarify the situation. So let's move on. First of all, I wanted to just introduce one slide for motivation. And this comes from the Intergovernmental Panel on Climate Change report from 2007, showing global energy flow from 2004. I have searched for more recent data, but typically it's only available on a per country basis. Lawrence Livermore National Labs in the US does publish this information annually, but they tend to show it in terms of import and export from the US and internal to the US. But this is international. Some of the things I wanted to point out about this diagram, this is known as the Sankey diagram. It's a useful way of showing how information is related in different areas. So on the left, we have the known reserves of various kinds of fuel. Then we have the amount of energy or flow called conversion on an annualized basis. And this is in exajoules per annum. An exajoule is 10 to the 18th joules, so quite a lot. Also, there's in this diagram, it's showing CO2 production, but I'm not going to talk about that in particular. Also, the diagram shows where the energy ends up being used, primarily breaking it into transport, industry, buildings, and losses. And a particular interest to us is electricity production. And this is showing that 173 exajoules of energy went into electricity production, but the output in that energy was just less, a little less than 50 exajoules. And so from my calculations, that means the electricity system is roughly 29% efficient, or if you include the heat output from the CHP plants that's used mostly in Europe, it's maybe 35%. So the majority of energy going into our systems is going into losses. So that's, I find a bit disturbing. So we do need to think about our efficiency, but we also need to be looking at how we can introduce more renewables. And I believe the smart grid is a way of strengthening the system to allow the adoption of more renewable energy resources and reduce our reliance on fossil fuels. Another observation is that half an exajoule of the total electricity production was used for transportation, whereas the total transportation consumption was 80 plus exajoules. So this means that if we could convert all transport to electricity, we would have to increase electric production by an additional 160 or so %, so 2.5 times current usage. It's possible, maybe, but it's a stretch. Anyway, that's just one thing to keep in mind. And I think it's always a motivation to think about how we can do things better, do things more efficiently, and do things in a more sustainable manner. So the smart grid, I believe it's a complex system of systems which themselves are all complex. So what is it? Some people say, well, it's SCADA on steroids. It's beefed up SCADA. And some people say, no, it's SCADA on methamphetamine. It's just running around in circles and trying too hard. But I think it's really more a combination of politics, engineering, and salesmanship and money. And it's often to do with what government regulation is or government incentives are offering. And at least 15 years ago, smart grid seemed to be thought of as being smart meters, because that was what was available that you could buy. And the governments were saying we need to do smart things in the grid. And people said the only smart thing I can do better than I'm doing now is a smart meter. So smart meters were smart grid for a few years, but that will change over time. The smart grid, I think, is enabling technology driven by other requirements. So those are the important factors. So what are those things? And I think it permits the increased use of renewable energy, and that's a primary motivator from my viewpoint. It also should enable the improvement of the reliability of the energy system. And we should also be able to reduce losses, firstly by reducing efficiency, but also by being able to monitor basically electricity theft, or known as non-technical losses in the industry. So smart grid, it's a combination of the traditional power system and the various components and players in that system, and a communication network working with that system into a combined data and energy system. This also enables certain things to be done if we have more information and it's up-to-date information about system. So we can run simulation studies and identify correctness of our data, do scenario testing, contingency evaluation and so forth. We can improve the reliability of the operation of the grid because we have more monitoring closer and closer to the end consumer. We should be able to improve efficiency and optimize the operation of the network because we have more information about how it works. And especially in the United States, there's a lot of focus on the way the market operates and enabling people to have more choice in how they consume energy, when they choose to consume energy, and to relate that back to the providers of energy and the financial transaction for how that all works. So there's technical components, there's commercial components, there's system marketing, various different parts to be considered. Physically, we have two parts to this. We have the traditional electricity part of the grid, mostly shown on the left. And then we have some communications infrastructure with various different elements shown on the right. So this spans from the wide area networks through to our industrial style networks, what we presently have with SCADA systems in a field area network, and moving into automation in the consumer's domain, which might be building automation or even home automation as one of the end goals. So this is what is perceived as being the collection of things going into smart grid. So the smart grid should make the power system more efficient, more reliable, etc. And it needs to operate from readily available technologies. We cannot wait to invent new magic things. It has to work on what we have. and I believe we have technologies to manage this. It should follow recognised standards which simplify the integration of various components. And we also need to secure and protect the information that manages the grid. And in some countries, there's a lot of focus on personal information and how that needs to be managed. So it needs to be self-monitoring and self to improve security, etc. It also needs to be upgradable and extensible. Okay. So the cost-effective component is interesting. The concept is that if we do this properly, we should be able to have a more efficient grid that runs more effectively and more cost-effectively. And the interactive component is to meet some market expectations to allow consumers to choose how they get energy and to allow new participants to provide energy to the grid. I'll leave this up for a moment so you can read it. Essentially, the idea of the elevator sales pitch is if you get into an elevator with someone who says, what is smart grid? You have the time it takes the elevator to travel 2 or 3 floors to tell the story, and that's all the time you have. So these are a few key points about the claims for the smart grid. Improves, lowers the cost, makes it more reliable, should prevent blackouts, should allow integration of renewables, and make it more cyber secure, is the summary. Many of you will have seen these diagrams published by the North American National Institute of Standards and Technology. A friend of mine was responsible for creating these diagrams, and I've found them a very useful tool to explain the concepts of the architecture. So there's a conceptual model with a combination of the different actors or domains in the system, which have communications between them to share information and data about how the system is managed, together with the electrical connection between the generation, transmission, distribution, and end users of the system. Now, there are lots of elements to this, and I have not included them all in this presentation. But just to give you an overview of a few of them, there's the idea of looking at the overall conceptual model being created with a set of domains. And so, for example, this domain diagram in the middle is the transmission domain, showing substations, transmission lines, energy storage, and communication and monitoring for switches, meters, breaker position, phase angles, watts, VARs, etc. So certain data being available and communicated with the users and shared with other domains as appropriate. Within some of the higher level domains, the operations and the market domains, for example, there's also a lot of detail about the various functions and interfaces that occur within that domain. And the blue lines, like a network diagram, showing the kinds of data that might be shared between these different applications that operate within that domain, and how they then share data with other domains as well. The market operator is sort of a commercial layer above the network, and this is not an area that I deal with directly, but it's all part of the integration of all parts of the smart grid together. So the market operator, the planning, scheduling, and so forth, and the bidding to supply energy or consume energy is handled by the market operator, who then communicates with the operations divisions who actually manage the transmission and distribution and so forth. There's also an entity in this architecture of a service provider, which might be part of the distribution utility, or it might be a separate entity who's responsible for managing the customer's information and so forth. So they interface with information from the customer, from the meter readings and so forth. They interface with the operations from the distribution network. They interface with the market operator to do with pricing and so forth. And they also probably look after maintenance issues on the network, etc. And they might gets down to the level of actually managing the automation systems within buildings or homes to help manage the efficiency or the economy of the network or manage the demand of the network. There's an organisation called the Gridwise Architecture Council who have published a model of how they see this operating, and it is broken down into multiple levels, essentially coming from regulatory and economic levels at the top with the political objectives or the regulations that the network is required to operate to, going down to the business operating rules that each utility might introduce to meet those objectives, then going down to the actual data that we use within the system. So the data we use has to match up with those business rules. We have to get the data we need to support the functions, etc. And to get that data, we have to have a shared understanding of message semantics and data semantics so that we understand what we are conveying. And that then comes down to the actual technical interchange of data using typically standardized protocols and established mechanisms to define what we are looking at. And across all of those levels, we have things like cybersecurity, we have things like time management, auditing of data and logging of information and so forth. So there are some things that go across the layers and some things that live within the layers. It's just another view of how to break down the complexity of all that we need to do into manageable pieces by separating them into separate layers. And from all of this, NIST developed in cooperation with the Electric Power Research Institute this smart grid architecture. And this is an example of how it might work. And this shows, again, the various domains, market operations, etc., and things like the transmission and distribution networks interconnecting with the operation centers for those networks. And it shows the data interfaces between those different domains for different purposes. And here's a particular example of what that might mean. And my friend who drew this diagram tells me, make sure to emphasize this is just an example of how it might work. Each utility or each system will choose to do the things that are needed to meet its business objectives. So in this example, the consumer is going to take part in some new energy program from the service provider that gives them a lower cost of energy or allows the service provider to reduce their demand if there's a shortage or a potential blackout. The service provider advises the distribution company that the customer has enrolled in this program. Once that's done, if the market operator identifies that there needs to be a reduction in consumption, they issue a signal to the operations. That might be a price signal or it might be a maximum demand signal, but some message to say reduce the demand. The market operator connects that to the metering system to issue an announcement across the distribution network, which ends up with the energy interface at the consumer that interfaces to this. It receives the signal and it knows to take action to somehow reduce the power consumption. If this is done, that system then feeds back to the operator to say, yes, I have done what you asked me to do. And that signal goes back to the customer management system to indicate that the customer has participated in the activity, and that then alters their consumption price in the next billing cycle, going to the service provider who then sends the bill to the customer. So that's an example of how this might work for one specific case of the customer engaging or enrolling in a demand management service. And for this to work, we have various communication protocols being used. So for example, markets to operator might be running over the internet. It probably is running over secure HTTP, probably with XML, probably with a RESTful interface in the applications. Within the distribution system, we are probably using the IEC 61970 and 61968 SIM models, which are used as an enterprise bus between the various EMS and DMS applications. We are probably using typical wide area network Ethernet style things, SONET, maybe various kinds of communications across the distribution network. And then we end up talking to the building network or the customer premises, which might use Wi-Fi or BACnet if it's a commercial building, or Zigbee or some similar mechanism for the devices in the home or the building to communicate and participate in this control. So it's a complex interaction just for a simple application like this. So the message from me here is there's lots of different actors, lots of different systems, and they need to integrate together. So over time, these different applications and domains have evolved their own special way of doing things, and they've got to now be integrated together. And so we need to learn to work with each other. And sometimes we need to change or expand what we've been doing. So some of the interfaces, especially the communication interfaces, have been IT-centric, and some are OT, operational technology centric. So the traditional SCADA style systems or intercontrol center protocol. And cybersecurity has to run across all of those things to ensure that the right data gets to the right people in order for them to perform their job, but also to protect the data from being inadvertently or deliberately changed by someone who is not authorized to do that. So that brings us to cybersecurity. You will often, or I often see people talk about the Purdue model, which is not actually a security model, but it's often a good way of looking at a control system architecture, much like the OSI interconnect model is a good way of looking at protocol stacks. So within this model, we can see that there are several different zones. So there's the head office zone, the corporate network zone, which is where planning often occurs. And there's a manufacturing zone. So this is a factory focused kind of model, but it says we have things like the control system, we have SCADA and the control functions. And they're often separated by some kind of demilitarized zone to separate the networks and to be able to monitor the traffic between those networks. Typically, we also separate safety functions, and in the power industry, think of protection as being the safety function, equivalent to an oil refinery emergency shutdown system. So the safety zone is often separated from the manufacturing zone, even though they may physically be in the same place. And within the manufacturing zone, we might have subzones of things that get grouped together. And the idea with the zones is that we should be able to monitor the traffic flowing between the zones and to firewall that traffic and ensure only authorized traffic goes between the zones through designated interfaces called conduits. So this architecture helps us to identify where the information flow should happen between these different kinds of places. So the US Department of Homeland Security has a recommended architecture for control systems, and this diagram comes from them, and it's published in the NIST publication, special publication 800-82, which is freely available on the web. It's a good resource for control system cybersecurity. It is specific to control systems, and it has lots of recommendations. And it's good reading for anyone who wants to work in the cybersecurity space, because if nothing else, it gives you a checklist of things to consider if you should take that action, or if this is something that needs to be considered for the system that you have. Anyway, this architecture is very strongly showing all the firewalls and the blue circles, the blue dots on the communications network, which are the monitoring points. And so the firewalls are basically controlling the access between the different zones of the system, and the IDS monitoring, the intrusion detection system monitoring, is there to identify any unauthorized traffic and alert on the traffic. Some people like to, and especially in the IT space, they would prefer to put intrusion prevention systems, IPSs. I think there's risk in doing that in a control system because there are some times when there is an unusual message which is required for an emergency situation, like a shutdown message, that would possibly be blocked by the IPS. And because it's an unusual message, it thinks it's an attack. So there's a lot of decisions to be made during cybersecurity design. So the zone perimeters, people often think of them as being essentially between the corporate IT and the SCADA system, so the IT-OT interface. But they often forget that our SCADA systems typically talk over commercial communication systems, third-party communication systems. And so there should also be management of that interface anytime it goes across a boundary outside the organization. Also, in most of our systems, we have connections to third parties, such as the equipment manufacturer, who will provide maintenance functions by connecting into our system. And in Australia, for example, the government has recently legislated to prohibit permanent third-party maintenance provider connections from outside of the country. Now, this is largely, in my view, a legal problem. And the reason they've done this is because if they discover that an external party had installed something malicious in a control system, if that third party is overseas, they have no legal jurisdiction to take action about it. But if it's inside Australia, they basically can go to the court system. So it's partly legal and it's partly technical. So just be thinking about those kinds of connections that may not immediately come to mind when you look at the Purdue model. Also consider segmentation of the various separate parts of the network. And if they are not equal in terms of what they should be doing, then you should monitor and control what data can flow between them, determine what data needs to go where, and verify that only that data is flowing between those parts of the system. And it's one way of doing this is to enforce a change of protocol before crossing to the next conduit, which means you have to have explicitly done something to configure how those two parts work together. And that probably gives you the scope to actually control what can be done across that. And in my view, encryption is a very bad thing in this space. And the primary reason is if you cannot identify what an encrypted packet is, you have no idea if it's valid or if it's malware of some kind. So my brave statement to you is anything encrypted is malware until you can prove it is not. So authentication of data is very important to ensure where the data comes from so that you know it's authorized, but encryption of data is a challenge. Sometimes encryption is needed. Sometimes you do need to keep the data secret, and there are other times and other applications where encryption is useful, but it is not the simple answer. And I say this because I've met people who simply say encrypt everything because for them it's the simple, easy answer when they don't know what to do. And I say it's not a good answer. You should know what you're doing. That's an opinion, obviously. Take that for what it's worth. So pulling some of these things together, to get security in our systems, we need to consider both security needs and operational needs. And in general, correct operation of the system will override a security requirement. Because if security stops the operation of the system, typically the security will be bypassed. And that's just the reality of how people work in the world. So make security happen automatically and make sure that it does not impede anything from working the way it should. Also, there should not be any direct path from IT to OT, because the IT network of a utility is typically in the end connected to the internet. So if someone comes in through the internet onto your IT network by breaking through your firewalls or sending someone some phishing email and dropping some malware, that should not allow them to then connect to your OT network. All communication by users out to applications should be verified. There should be role-based access control. And that means you need to identify who is connecting to the network and know what they are permitted to do, and only allow what they are permitted to do and see, and prohibit them from doing things that they are not permitted to do. And sometimes, well, wherever you have an interface, check what's going over that interface, and only allow the valid traffic. And in some control system protocols, it's very easy to view and identify what the traffic is, because it's very consistent across time. And so we can set up rule-based systems that do this quite well. It's much easier than in the general IT space, where there are many applications and you don't know what the traffic will be. Over the last decade, we've seen an evolution in the interest in cybersecurity, but it's still a moving target. You need to identify for each utility what kind of approach you need to take, whether you're going to focus on certain areas and do it small step by small step, or try and take a big leap and migrate from an old type system to a new type system in one go. There are many equipment vendors out there who can supply various kinds of tools, like intrusion detection, unidirectional gateways, often called a data diode, things like deep packet inspection firewalls that look inside the messages, and they can actually look inside, for example, a Modbus message, and they can be constrained to only allow a certain command to a certain register, and only those commands are allowed through, for example. So you can tighten them down quite strictly, but it takes a lot of engineering and configuration and knowledge to do this correctly. So a bit about cybersecurity. Every system is going to be somewhat different. There are different regulations you need to meet. There are different combinations of things in the system, different brands of equipment, different kinds of equipment. Some is old, some is new, some different communication systems, and so forth. Every system is different. And so whenever you ask questions about, for example, what should I do with something, usually the answer from someone who knows what they're talking about starts something like, it depends, because there are many variables that need to be considered in order to answer a question like that. There is no case where there is one correct answer that always applies. But in this space, following the standards does tend to make your life easier, rather than having to reinvent everything every time. So the important steps with cybersecurity are determining the policy. So the policy says what kinds of things you're concerned about managing and securing. And part of the policy needs to be the periodic review of that policy to ensure that it's still current, that it's still applicable, and that you don't need to make changes. Once you have a policy, that's going to guide you in what kinds of things you might need to focus on. And that then determines what kinds of procedures and maybe what technology, what kinds of tools might help implement those procedures. Then you deploy that, you implement it, and then monitor how it works to verify that it is actually doing what you expect. And then go back to the beginning and check if that is matching what your policy says, maybe update the policy and go through the cycle again. It's an ongoing cycle. So you should have ongoing review built into the procedures as part of the process. That's one of the ways of doing this kind of thing. So protocols and standards. There's lots of protocols out there. There's always a reason for this. And our friends from XKCD caught that quite well. When you've got 14 competing standards, you need to fix that by having one universal standard that covers everyone's use case. So then you get 15 standards, of course. That's how it happens, and that's the reality of the situation. Some of these standards seem to look very similar, but many of them are very specific to the application domain, and they are not always interchangeable, even when they look like they're doing something very similar. There's a lot of detail. And you have to typically learn a lot to truly understand what's going on. And again, it's like a tool. You have to use the right tool for the job. So think, hammers work with nails, screwdrivers work with screws. You can hammer in a screw. It's not a good thing to do. It's very difficult to get a screwdriver to put a nail into a piece of wood, but you can do it if you try hard enough. So use the right tool for the job. Find out what the tools do. That will help you. So what are we doing? Well, every application can be different. And I want to start with a simple example. So for example, in a room, we have a light bulb in the room and we have a switch on the wall. And normally we go and we press the switch and the light comes on. That's a pretty simple system. And I think we all appreciate that all that needs is a source of energy and some wire, and job is done. Very simple system, very easy to implement, fairly intuitive. We don't need a complicated standard or a lot of guidelines to do that. But what happens, when we have 2 switches and 2 lamps? Well, we just do the same thing twice. That's pretty easy. That's okay. How about we have 100 lights? It gets more complicated. We might begin to think about whether we need to do something better than 100 wires and 100 switches. And especially if the lights are actually in a town 100 kilometers away that we're controlling remotely, then we need some different kind of technology. So this is where we begin to have support frameworks. And so if we started off with that example, we have a simple system with no standards. And when the system is simple, the complexity is low. But as you increase the complexity, the amount of effort involved when you have no standard becomes higher and higher. If you adopt some kind of framework that provides services, you can end up having a more complex system that is still manageable because you use a framework that supports various functions. And perhaps you have a rich standard that provides a lot of features and therefore does a lot of the work for you. But typically that rich standard is more complex and has more options. And it means that it's more expensive to use it for a very simple system, but it's the best approach for a very complex system. So you need to make an appropriate choice of whether you choose just do it with no standard, to use some simple standard that helps, or a complex standard that provides a lot of services but is complicated to learn. There's also the case where you could choose some inappropriate standard that is itself complex and does not really provide services to support what you're doing. So again, you need to understand what kind of functionality is provided by the different standards and which ones suit the application you have. So start with the functional requirements of what you're trying to do and identify if some existing standard that's usually used in the domain supports what your requirements are. Sometimes there will be no standard that actually exactly matches what you want. In that case, you have to consider whether you can use one of the existing standards and then do some extra work to meet your requirements, or if it's easier to develop a new standard that will meet your requirements and then require that everybody adopt that standard. So both of those work, but I will make the assertion any system can be made to do anything if you apply sufficient effort and expenditure. So you can force any standard to do anything by adding extra engineering to it. And secondly, it is not wise to adopt a standard just because somebody else uses it if it is not working for you, if it does not help you with your application or your requirements. And this is a complicated one because there's a lot of pressure from the industry to adopt the new standards, sometimes without truly understanding if that's a good idea. So there's a little bit of guidance available from the IEC standard document, which provides the reference architecture for the Technical Committee 57, which is the committee responsible for all power grid communication. And it describes their plan. And the idea they have is that for every function, there is just one standard. So the diagram on the left shows a substation at the bottom, a SCADA control center in the middle, talking to another control center on the right-hand side, substation to substation communication for protection functions, for example. And then on the left-hand side, there's hydropower plants and distributed energy resources connecting in as well. So there are various protocols and standards that appear here used for various functions. And the present statement from the IEC is that if you are talking about modeling the power system, you should refer to the SIM models, which are the ones that live within the communication bus interface in the control center, 61970 and 61968. And if you're talking about the actual communication between devices, then they are basing everything in 61850, at least conceptually. Now, for a certain level of complexity, that is great. But 61850 is the most complicated thing you'll ever meet, in my opinion. And it is very complex and very difficult to learn. And if you think you understand it, you are mistaken. It's like quantum physics. When you think you understand it, you're wrong. You don't. It's got more parts to it than you can imagine. Anyway, that's an exaggeration. Of course, if you spend a decade or more, you do get to learn most of it. But people seem to think it's very simple, and that's not the case. So for some applications, 61850 is too complicated or too expensive and is not appropriate. For some applications, it provides a lot of good services and is almost the only way you could afford to implement certain features. So some protocols you probably have never seen in the power industry because they live in the industrial plant, but you'll hear about them a lot in control system cybersecurity discussion because they're very common in factory automation, oil refineries, that kind of thing. Electric power often needs to know about time series history, and that's not often that common in other industrial applications. Also, the DER applications need to, or introduce this idea of enrolling a new DER. So we have to be able to simply connect a new generation resource to the network without a lot of complexity. And that's very different from our substation or power system type devices where there's a long planning process to introduce a new piece of equipment, and it's planned, it's scheduled, it's configured, and there's a lot of integration testing that gets performed before it's actually commissioned. Not the case with DER. That is more like potentially a plug and play kind of system. So some brief high-level overview. 61850, it was originally designed for use in the substation. It's now being promoted for use externally across all power grid functions. 61850 created the Goose and sampled value protocols because they had requirements that no other protocol could meet. So here's an example of creating something if you need to because nothing else will do the job. It adopts MMS for some functions. MMS is a factory automation protocol. 61850 uses that for SCADA, and it is the second worst SCADA protocol in the world. It's the least efficient thing you can do, just about, but it can be made to do it. So my assertion, any system can be made to do anything. That's an example. The real strengths of 61850 are the use of the data models with very strongly defined semantics and naming, so that all of the data is associated with a name and the name is strictly defined. So once you see the name of some data, you can understand what that data represents. That's a great strength. Another great strength is a common configuration format in system configuration language, which is an XML-based configuration system, which is effectively a protocol for exchanging configuration data between the configuration tools for different devices and allows the integration of all of the devices' configuration in a single system configuration tool, which is a real milestone, and it does help manage these hugely complex systems. So 61850 is sometimes talked about as being the one tool for all functions. All I say is it does some things well and some things not so well. You decide, or you need to decide if that's appropriate for your functional requirements. Over time, it's being extended primarily with the addition of new data models for different domains and applications. But it is very complex and it requires a significant amount of training to use it effectively. So just be warned about the common information model standards, 61968 and 61970. They're designed to interface the EMS and DMS applications in the control center. And they define a model describing the power grid itself, not the communication, but the grid. And they allow those various functions at the control center to share information about the operation of the grid. Those models do not exactly match the data models in 61850. And so if you get field data in 61850, it requires some manipulation before it can be put into the SIM models. The intercontrol center protocol is, again, for communication sharing between control centers, basically to update the neighboring utility or a higher level regional monitoring utility of the state of the SCADA system below the control center. It provides some level of SCADA-like functionality, but it cannot typically be used in place of a SCADA protocol because it does not provide the same kind of interactive level of event reporting that a SCADA protocol typically will. 60870, 101, 104, they're electric power SCADA protocols widely used in Europe, Asia, and South America. It's based on a report by exception data model, which basically means you only have to transmit data that changes. Everything that has not changed, once it is transmitted once, it only has to be updated when it changes. IEEE 1815 or DNP3 is the equivalent SCADA. It's used almost universally in North America, Canada, US, all of Australia. It's used in the UK distribution system. So I say it's a largely English-speaking country protocol. It's used in about 30% of utilities. Originally designed for electric power applications, so it does the same kinds of things as 101, 104, but it's a general purpose SCADA protocol and is very widely used in the water industry as well. Again, based on the report by exception model. You will sometimes see Modbus for simple applications or talking to PLCs. Modbus does not have a report by exception kind of model, has no event history kind of model, but for simple applications, it's easy to use. For more complex applications, it quickly becomes expensive to engineer because of the way that the data is typically used by most devices. But I don't want to spend time talking about it. In the DER space, the IEC has a set of data models for DER, and that was presented in the it's a conceptual diagram of the interfacing of protocols I showed earlier. The Smart Energy Profile is an IEEE standard that is for DERs. It maps onto those data models from 61850. It adds the enrollment functionality for adding new DERs and has scheduling functionality that is not a common thing in SCADA systems. So the scheduling might allow the DER to operate in different modes at different times of day. Based on standard IT practices, it transmits XML over HTTPS, so it can run over the internet. In North America, there's a couple of organizations, SunSpec, who are mainly a solar panel organization, representative body, and MESA, the Electric Storage Association, who look after battery storage. And they've released a profile of DNP3 that maps onto the 61850 DER models. And the idea is the aggregator can control individual inverters in a household, for example, with Modbus, brings the data together and collects it and then interfaces to the utility with DNP. So typical characteristics: electric power and real-time SCADA protocols have a low latency. They report data in event time sequence for critical applications. They've got a high reliability for reporting and a very high control integrity, so the chance of an incorrect control operation is very low. Protection communications within the substation, this is where Goose operates and does the wonderful thing that nothing else can do. It has very short latency between protection devices. Between substations, we can typically operate in about 1 or 2 main cycles, something in the order of 20 to 50 milliseconds. These systems also need high reliability and self-monitoring to identify if they have failures. Smart metering, latency is typically not an issue. They often use mesh-based radio systems that transmit data from one device to the next and it then forwards it to the next device, etc. The communications networks for smart metering are often optimized for that application and they're not often useful for doing other things. So people think of putting SCADA functionality over smart meter networks. It's often not possible, or sometimes it's not possible to do that. And then with the automated building, automated home concept, there are smart devices within the home talking to the smart meter, and they might use Wi-Fi or Zigbee or something like that. BACnet is often used within office buildings and for building management systems, looking after air conditioning and lighting and so forth. And these systems then interface with the smart meters and so forth to participate in the various functions. So in addition to all of that, we have the operational data, but we also have asset management data, we have configuration data, and we have software and firmware in these various devices. Now, some devices allow that information to be available over the same runtime SCADA type protocols, but generally they have some kind of proprietary interface and there's no standardization in that space. So, and software is typically proprietary to the device as well. So we have standards for some things, especially the runtime or real-time data, but not for this other kinds of data. So we also need typically to have engineering access to devices, maybe to retrieve fault files or to download new configurations or something like that to do remote maintenance. And that's typically accessed and controlled by passwords. And we need to manage those passwords, change them periodically, revoke the passwords, etc. Again, that's all done in a proprietary manner. There's no standardization of that. So the runtime data is well standardized, the other data is not. There are ways of mapping between various kinds of data. So 621.850 can map onto the 60870-5 SCADA protocols, and there's a standard technical report -90-2 explains how to do that. In the same way, there's a mapping for 621.850 to DNP, and it's also possible to use 621.850 directly from the substation to the control center. So there's lots of ways to transfer data between protocols and map them directly, but there are some pairs of protocols that simply cannot have data mapped between them without loss because they have different underlying models of how they operate. So sometimes you lose information unexpectedly. You lose timestamps, for example. In every case, the protocols work best when they're doing what they were designed to do, whether that's distributed control systems in factories, SCADA, substation automation, or whatever. And if you understand the limitations of each protocol, you can avoid the traps. But if you don't know what they are, it's easy to get caught out sometimes. Okay. One of the issues I often see with mapping between protocols is that sometimes, especially, you lose timestamped event data, and the only time you can identify that is when the information in the SCADA historian does not match a log extracted from the field device because something got lost. And there's typically no way of identifying that it got lost. It's just because of a fundamental design mismatch between the way some protocols work. So you cannot always get everything just the way you expect unless you're prepared, for example, to introduce extra delays. So that was a jump across a lot of different things. So I'm just going to suggest to you that we should learn from what's gone in the past as we look to the future. So history doesn't repeat necessarily, but it seems to rhyme sometimes. So Winston Churchill said, the farther you look back, the farther forward you're likely to see. So if you know your history, you can prevent making the same mistakes. And Isaac Newton wrote to Robert Hooke and said this famous statement, if I have seen further, it is by standing on the shoulders of giants. So we learn from where we stand now and what we know now, and we look to what's next, and we invent the future as we go. So let's go forwards, not backwards. So the history, SCADA protocols. In the late 1960s, this was a new thing. Several vendors had products that had SCADA built into them, and they were all proprietary. So vendor A had their kind of device that spoke their protocol to their master station. And vendor B had the same kind of thing with their protocol, and vendor C had their protocol, and vendor D had their protocol, and vendor E, etc. So they were all different. They all did much the same thing. Now that's okay if you only use one kind of product. But the industry, the utility said, no, we want to get the best kinds of products from each different company that do the job we want to do. And we don't want to be limited just because of the communication protocol. So a way to do this in a universal manner was to introduce some kind of data gateway that converts the various proprietary protocols onto the system protocol. And it's really good if that's one of these standard protocols. And it's even better if we're using standard protocols from the devices themselves, because that simplifies this whole process. So we've learned to do this kind of thing. So the timeline for this, 1960s, was the evolution where these new protocols were being developed, probably as a result of telemetry from satellite monitoring and that kind of situation. Products were becoming available. Everyone had their own solution that looked fairly similar in terms of functionality, but was simply incompatible with each other. By the late 1980s, the utilities were saying, we don't want any more proprietary systems, we want standard interfaces. And that led to the development of 60870 and DNP and the utility communications architecture, which eventually got handed across to become part of 61850. So these days, we assume that's all fixed and everything is interoperable. Now, let me just say, conformance testing really helps. People still manage to misunderstand things in the standard, or the software guys make mistakes and there are bugs in devices. We still need to test devices, and standardized conformance testing is one way that helps ensure that what a utility purchases does in fact operate. The year 2000 or thereabouts, wind farms were the new thing. So again, a new area, people were inventing new things. Everyone had their own way of doing things and their own way of interfacing the control information. Similar offerings that were incompatible. And again, in about maybe 5 or 10 years, the marketplace demanded interoperability, leading to the development of some standards for wind farm control systems. More recently, we have seen the development of solar panels with inverters, battery storage systems, and that kind of system. Again, lots of vendors in the marketplace, each developing a great product, each doing it their own way. Similar offerings, same kinds of functions, but not interoperable, not compatible. So the marketplace decided again it was going to demand interoperability, and we've seen the development of various standards, such as 61850, Part 7, Part 420 with the DER models, the SEP2 standard, the IEEE 1547, which is used in North America to set the operating rules for connecting DERs. Right now, we're seeing the industrial Internet of Things emerging. Lots of different vendors, lots of great new devices doing really clever things, lots of special secret stuff built into them. So we are just beginning to see, as people begin to adopt some of these devices, they need them to integrate into the systems they already have. So we're now looking at how we can integrate all of that. And some of these vendors really do reinvent the wheel. And I was amused to see someone announce a few months ago that they just figured out a new way to control generators that was exactly the same as something that I'd seen from 1968. So it's the same thing coming around again. If you know your history, you can approach things more sensibly. All of this with IoT typically is looking at the internet, and so security is an issue there. So all those things, we've seen that in the recent few decades, different domain areas having the same kinds of issues. But we are getting better at more quickly identifying that we need to standardize things. So my question, what's next? What should we be looking for and get ahead of this curve? And I think device management is an area that needs to be addressed, because that's the space right now where there is no standardization. But the question is that even practical? Because one of the benefits from device management is that vendors introduce new technologies, new ways of doing things that needs to be managed by them in their own way because nobody else is doing that. It's not part of any standard. So we cannot expect those standards to emerge before the concepts of what they're supposed to do. There's a bit of a chicken and egg problem there. So right now, devices have proprietary maintenance interfaces and protocols and proprietary tools. There is some standardization. So for example, right now, there is work in progress to develop a 61850 part, which talks about managing file transfer, configuration, and software updates in 61850 devices. But it does not do some of the other functions, such as remote engineering access for maintenance, managing device passwords, etc. So we still have other areas of concern. So challenges, we've got lots of different kinds of information. Some of it's real-time and operational. Some of it is historical. We've got event logs, fault logs, etc. We've got asset management information. We've got configuration data, settings data, firmware changes, all kinds of information that some device might have. There are lots of applications for using that information. So the real-time data goes to SCADA. Asset information goes to the asset management people or the maintenance depot, etc. The fault logs might go to the protection engineer to analyze them after a fault occurs. The relay engineer might need to get access for engineering to change the configuration, change the settings, and so forth. Each different user has a different need for access. So each stakeholder has some business reason for their job to access some subset of data, and each should be protected from accessing or changing things that they should not be able to touch. Also, we have the life cycle problem. In our system, we have short life cycles in the IT space typically, and longer life cycles in the field device space, and a third life cycle in the communications equipment, which is sometimes fairly short as well. And it's been somewhat surprising to me, at least, how after many years of very stable communications, we are now migrating versions of technologies in the communication space almost faster than technology versions in the business intelligence space or the control center space. So the communications network is now becoming one of the areas of complexity. Sorry, I just had push the wrong button there. No, it didn't. Sorry. Okay, so we have this integrated system. We've got field data from various devices. We've got the comms network in the middle, and we've got various users at the control center or other business applications in the corporate space. They could all get data from any of the devices, and each device could have any kind of data to be given to those different users. So we want to be able to integrate data from all applications. We want to have the correct people access the right data. We need role-based access management. We want to be able to securely manage everything in the device, including configurations and passwords, and everything needs to be auditable for security. So this is a North American regulatory requirement that anytime anyone touches anything on the network, there is a trail of who did what and what was changed. So this brings us to a sort of a collective view of what our power system network might look like. And so, for example, we have substations with various kinds of equipment from various manufacturers doing lots of different tasks. We have different kinds of communication protocols. Some are serial, some are running over Ethernet. We have some kind of an RTU or a substation gateway or a protocol converter of some kind connecting off to the wide area network, going to different applications. So some data, the real-time data, goes to a SCADA system. Other data might go to various applications like historians or asset management, etc., or it might go to a fault record analysis suite and so forth. Different applications need access to that different data. And we also have a distribution network where we don't have substations, we have individual devices spread around our networks. And those individual devices may have the same kinds of information as the substation devices. So we need to be able to do this not just through a centralized data gathering gateway at the substation, but across the overall network. So we need to be independent of the manufacturer of the equipment. We need to be able to cope with whatever it is we have. And in the real-time space, the SCADA space, we have good standards for that. But in device management, that is still a challenge. Okay, so device management is probably the next area we need a consistent approach. And we are going to have existing equipment in place for many years. So we need to be able to manage what we already have. We cannot just change everything to the next generation in one go. Each different user has different requirements to access things, and each user should get secure access to what they need. So where will this go? From Star Wars, Yoda had a wonderful way of saying things. Difficult to see, always in motion is the future. But my friend Winston Churchill put it differently, said, though imminent, the future is obscure. We're not really sure what's going to happen, but it's coming close and coming fast. So if you need to contact me, my contact details are at the end of the deck. And with that, I am complete, and I thank you for your attention. And I'm hoping at this point, Dr. Sambandan might take over and ask if anyone has questions.
Yes, sir. Yes, sir. Yes, sir. Yes,
Sure,
sir.
yes.
Yes, sir. Yes, sir.
Participants,
Dana,
if you have any, sir? Yeah. Participants, if you have any questions, you can post it in the chat box, or you can unmute yourself and talk. Is there any questions from the participant side?
Oh, they all fell asleep. Well, if I might make a comment, please understand that I've given a very high-level overview of a number of topics that relate to communications in the smart grid. I have not really given you any solutions or even any direct guidelines, perhaps, but I hope I have raised a number of questions that you will consider.
Yes,
Sir,
sir. Yes, sir.
if there is any questions from the participants, we'll just mail you, sir, so that you can reply in that.
That will work fine. Thank you.
Okay, sir. Thank you.
So,
Gayatri
sir,
ma'am?
it was a
Yes,
wonderful.
sir.
It was a wonderful presentation, sir. And
Yes.
as you rightly said, you have raised many issues open to thinking. And as you said, the future is always in motion. No, it's not. Nothing is precisely said. So future will decide how it catches up, and we'll have to work together to have a commonality.
Yes,
It's really
I agree entirely, and this is one of the challenges in this space in the industry. Is it does require a lot of cooperation between people and a lot of cooperation about how we do things. I think for some people that has been a challenging lesson, but it's also a wonderful thing to see, and especially the international cooperation between people trying to solve these challenging problems. So I'm encouraged.
yeah.
Sir, on
Gayatri?
behalf of KCG College of Technology, a special thanks to you, sir, for the wonderful presentation on smart grid, cybersecurity in grid automation, and the role of protocol standards, sir. I'm sure that our participant would get the maximum benefit out of this session. Thank you, sir.
Well, thank you for the opportunity, and a good day to you all.
Fortunately, I think we had a very good link also. It was also cooperating. The communication link was rather good. There was no major issues like we had earlier. Today it was a wonderful connection. It was we were able to hear continuously, and it was a. And even though you said your accent is quite okay for us.
Well, thank you very much for that feedback, and I'm pleased the technology cooperated with us.
Yeah, thank you, sir. Thank you, really.
Dear participants, I request you to all fill the feedback form and it accept the response till 12 o'clock only. So next session will start exactly at 12 o'clock.
Very good. But thank you. And with that, I will leave you. Good day.
Thank you, sir.
Good day, sir. It was good to see you.
Very, very obliged and very grateful. Really, indeed, a good presentation. And for us, it's a wake-up call to see that we see the future with more clarity. Thank you, sir.
Good. Thank you.